This book moves in three sweeping arcs, first zooming out to the largest cosmic scales, then zooming into the smallest quantum details. Finally, it steps back entirely, asking what all of that zooming in and out reveals about the true nature of reality itself. Think of the three parts as a road trip. You start from the highway of space, descend into the microscopic lanes, then pull over to ask where you actually are. The book builds a layered argument, introducing 4 different levels of the multiverse one chapter at a time, like floors in a very tall building. Level I covers copies of our cosmos far beyond the horizon. Level the second reaches into pockets of space with different physical laws entirely. Level the third lives inside quantum mechanics, and level I4, the wildest floor of all, says every mathematical structure is a universe in its own right. Quantum mechanics is at the heart of the book, and the author does not shy away from its strangest corners, including ideas like quantum suicide. Quantum immortality sounds like science fiction, but it follows logically from the rules of quantum theory if you are willing to follow them all the way. By not flinching at strange conclusions, the author shows you what it truly means to let the physics lead wherever it goes. One full chapter is devoted to the mathematical universe hypothesis, the idea that physical reality and mathematical structure are one and the same thing. This is not just a metaphor. The claim is that the universe is not described by math the way a map describes a city. It literally is a mathematical object. Reaching that radical idea takes the whole book to set up carefully, which is exactly why the journey through earlier chapters matters so much. The final chapter turns to life itself, asking whether human existence carries any meaning inside a cosmos this enormous and strange. It asks what the future of physics looks like, and how the universe itself might ultimately end, tying all the cosmic threads into one closing conversation. After all the equations and thought experiments, the book lands somewhere personal, reminding you that the person asking these questions is also part of the answer. This book did not spring fully formed from one mind in isolation. It grew slowly, fed by years of questions and encouragement from curious readers worldwide. People from different countries, backgrounds, and fields kept asking for these ideas in writing, and their persistent curiosity finally made the book happen. That global community of wonder seekers is really a silent co-author, proof that the hunger to understand the cosmos is deeply and widely human. 2 very different parents shaped the author's thinking. One sparked his love of life's big philosophical questions. The other passed on a deep fascination with mathematics. You can feel both influences on every page. The book is simultaneously a philosophical adventure and a mathematical argument, woven inseparably together. It is a reminder that the ideas we inherit from family can quietly steer the biggest intellectual choices of our lives. The author's sons Philip and Alexander fed him something no colleague could: the pure, unfiltered curiosity of children who have not yet learned what questions are too simple. Their genuine questions found their way into the book as real examples, showing that everyday wonder can spark serious intellectual work. If a child's question about the sky can end up in a physics book, it means no question about the universe is ever too small to take seriously. Before the book reached you, it passed through the hands of physicists like David Deutsch, Andre Linde, and Edward Witten, minds who could spot every error or overreach. Editors, family members, and non-specialist readers also gave feedback, making sure the ideas stayed both accurate and genuinely accessible. That careful review process is a quiet form of intellectual honesty, a signal that the author cared more about getting it right than about sounding brilliant. Above all the reviewers and colleagues, the author singles out his wife Maya as his muse and fellow traveler through every step of this project. That kind of personal, unwavering support turns a book about the cosmos into something intimate, a love letter written in the language of physics. It is a good reminder that even the most abstract intellectual journeys are walked, at their core, with other people beside you. The biggest lesson physics has taught us is deeply humbling. Reality, whatever it truly is, looks almost nothing like what we see in everyday life. Zoom in far enough and solid matter dissolves into empty space with probability clouds hovering inside it. Zoom out and familiar stars vanish into cosmic foam. Trusting physics over your gut feeling is not easy, but it is the entry price for understanding what the universe is actually doing. Thinkers across history have offered radically different answers to what is reality, from quantum fields to simulation theory to the view that the question is meaningless. That vast spread of conflicting answers is not a sign of failure. It is a sign of how genuinely hard and still open the question remains after thousands of years. You are entering a debate where no one has fully won yet, which means your own thinking still has room to matter. The author treats what is reality exactly like a detective mystery, gathering clues from experiments and following them wherever the evidence leads, even into uncomfortable territory. His childhood love of detective stories quietly shaped how he does science. Observe carefully, reason without bias, and never flinch from an unexpected conclusion. Questions like, how big is the universe? And what is matter made of? Are not textbook exercises to him. They are live mysteries he is actively trying to crack. As a high school student, the author actually disliked physics. It felt dry and pointless compared to the big questions swirling in his head. Then a turning point arrived. He realized physics is the deepest intellectual adventure available, revealing hidden layers of beauty inside ordinary objects like trees. Physics did not make the world colder or more mechanical for him. It made every single thing in it more astonishing than before. Most people think math is just a tool we invented to describe nature. The author goes much further, arguing the physical world actually is a mathematical structure. Nobel Prize winners have long puzzled over why math works so unreasonably well in science. The mathematical universe hypothesis offers a surprising answer. If reality is mathematics, then studying equations is not an abstraction. It is the most direct way to touch what is actually real. Every human culture across history has reached for answers about origins and the cosmos, yet their answers differ wildly, often shaped by local landscapes. Egyptian myths begin with primordial water, because the Nile defined life there. Norse myths open with fire and ice because Scandinavia's climate did. That diversity of stories shows the questions are ancient and universal, but the answers still wait for a method strong enough to settle them, and physics may be that method. Every time humans finally mapped the edge of the known universe, they soon discovered it was just a small corner of something far grander beyond it. From Earth being a planet, to the Sun being one of billions of stars, to galaxies clustering into walls and voids, the pattern repeated over and over. The lesson is not depressing, it is liberating. The universe is far more generous with its scale than we ever dared to imagine. Just as humans underestimated the universe's size, they also underestimated the human brain's extraordinary power to figure out cosmic truths from right here on Earth. Cave-dwelling ancestors already carried the brains capable of working out how old a star is, how far a galaxy sits, without ever leaving the ground. The cosmos was always within reach of the human mind. We simply needed the right questions and the right tools to unlock what was already there. Einstein's general relativity opens up two very different possibilities for space. It might stretch forever, or it might loop back on itself with no wall or edge anywhere. Picture the surface of a donut, travel far enough in a straight line, and you return home. Yet you never bump into a boundary-marked end of space here. Both options are scientifically legitimate, which means the shape of the universe is a real, measurable question, not a philosophical fantasy. The properties that truly define space, its dimensionality, curvature, and topology, are all mathematical in nature, with no extra physical stuff required to describe them. This is an early hint at the book's deepest claim. Space may not just be described by math, but may actually be a mathematical object through and through. If space is purely mathematical, then every room you have ever walked into is a geometric structure, beautiful, abstract, and utterly real. For centuries, people assumed Euclid's flat, infinite geometry was the only possible kind. It felt as obvious and necessary as breathing. Then, in the 1800s, Gauss, Bolyai, and Lobachevsky discovered entirely new geometries where triangles break the 180-degree rule and parallel lines can meet. Those discoveries cracked the assumption that common sense sets the limits of what space can be, and everything changed for physics after that. A 5-year-old asking, "Does space go on forever?" is actually raising one of the deepest open questions in all of physics, and no one has fully answered it yet. Whether space is infinite or finite connects directly to the possibility of parallel universes, making it far more than idle curiosity. Sometimes the questions children ask before they learn to stop asking are the very ones science most urgently needs to answer. Newton showed that the same laws governing a falling apple also govern planets in orbit, a single bold idea that unlocked the entire history of our solar system. Before that, nobody had a clue when the solar system formed or how. The question was not even considered a scientific one. Realizing that Earth-based physics applies everywhere in the cosmos was one of history's greatest leaps of scientific courage. Tidal friction from the moon has been gradually slowing Earth's spin. And working backward through that slowdown gave scientists the first real age estimate for the Earth-Moon system. The math pins the solar system at somewhere between 4 and 5 billion years old. Not eternal, not recent, but a specific number grounded in measurable physics. Finding that even planetary motion bleeds energy through friction was a quiet revolution. It meant the cosmos had a history you could actually read. Gravity pulled a giant cloud of gas and dust inward, and as it spun faster, it flattened into a disk. Our solar system is the leftover debris of that collapse. The fact that every planet orbits the Sun in the same direction is a direct fingerprint of that original spinning disk, still visible billions of years later. Astronomers watching other star systems form right now in real time have confirmed this picture. We can see our own origin story replaying around distant suns. The same gravitational collapse that built our solar system also built galaxies, just on a scale billions of times larger, and unstable enough to shatter into countless solar systems. Our entire Sun with all its planets is just one of hundreds of billions of solar systems tucked inside the Milky Way, itself just one galaxy among trillions. The same simple physics at work in a collapsing cloud on a Tuesday afternoon explains the large-scale architecture of the entire observable universe. Because light takes time to travel, every deep telescope image is also a time machine. Nearby galaxies are old and large, while the most distant ones look small and unfinished. Seeing baby galaxies billions of light years away is direct visual proof that the universe was genuinely different in the past. It is evolving, not static. The night sky is not a snapshot of now. It is a layered archive of cosmic history, with each distance corresponding to a different era. Even with all this progress, scientists openly admit they do not yet know what happened before Big Bang nucleosynthesis. The math breaks down before that point. Whether the universe had a true beginning, or whether something existed before the Big Bang, remains an unanswered and genuinely open question. Acknowledging the edges of knowledge is not a weakness in science. It is the compass that tells you exactly where to explore next. Cosmology transformed from a field full of arguments and guesses into a precision science the moment better telescopes and computers made accurate measurement possible. Debates that once raged about whether the universe was 10 or 20 billion years old were settled. Scientists now pin down its age to within 100 million years. The shift happened fast, within a few decades, because better data does not just refine old answers. It sometimes demolishes entire frameworks and builds new ones. When scientists measured the total mass of the universe, a shocking result emerged. Everything you can see, stars, gas, planets, makes up only 4% of what is out there. The remaining 96% is split between dark matter, which pulls galaxies together, and dark energy, which pushes everything apart. Neither can be seen or directly touched. We are, in the most literal sense, floating inside a universe whose dominant ingredients are invisible to every instrument we have ever built. The cosmic microwave background power spectrum is a kind of fingerprint of the early universe, and nearly every competing model of the cosmos predicts a different fingerprint. By comparing measurements against predictions, scientists have eliminated almost all previously popular models, leaving only one basic picture standing. This is science at its most powerful. A single observable curve capable of ruling out thousands of theories all at once. Three-dimensional galaxy maps revealed structures of breathtaking scale, including the Sloan Great Wall, a filament of galaxies stretching 1.4 billion light-years across. These maps show today's universe, while the microwave background shows the ancient one. Together, they let scientists watch billions of years of cosmic evolution unfold. It is like having both a baby photo and a current portrait of the universe, and being able to trace every change in between. One of precision cosmology's most stunning surprises is how well simple mathematical equations describe the universe from its first second all the way to today. Einstein's gravity equations work from millimeter scales up to the largest distances we can measure. The fit between theory and data is not rough, it is extraordinary. The universe has been faithfully obeying the same compact set of mathematical rules for 14 billion years, which hints that those rules are something very deep indeed. Even with all these successes, precision cosmology cannot yet explain what caused the Big Bang or why the early universe had its very specific starting conditions. Nobody knows where the tiny 0.002% density ripples that seeded all galaxies came from. It is a gap the size of a crater right in the middle of our best theory. Those unanswered questions are not dead ends. They are precisely the places where the next great leap in physics is most likely to happen. The standard Big Bang model sets the universe off from infinite density with no cause, no mechanism, and no explanation for why space was already infinite at the start. Alan Guth studied those unexplained assumptions and found the story awfully contrived, a polite way of saying it was full of holes big enough to drive a galaxy through. A good scientific theory should explain, not assume, and the Big Bang model's starting conditions were assumptions dressed up to look like explanations. Opposite sides of the sky have temperatures that match to 5 decimal places, yet in Friedman's model those regions could never have communicated with each other. Imagine all your friends independently sending you a lunch invitation at the exact same second without ever talking. That is how unlikely this temperature match really is. Something must have coordinated those distant regions, and the standard Big Bang simply had no answer for what that something was. For the universe to stay nearly flat for 14 billion years, its density in the early moments had to match a critical value to at least 24 decimal places of precision. Tip the balance even slightly too high, and the universe collapses back on itself in a big crunch long before any stars form. Tip it too low and everything freezes in a cold void. Friedman's model offers no reason for that knife-edge precision. It simply happened, which is scientifically about as satisfying as saying because it did. Alan Guth's inflation theory proposed that a tiny, uniform blob expanded exponentially fast, doubling in size again and again in a tiny fraction of a second. Because all distant regions grew from the same tiny starting blob, the horizon problem dissolves. Of course, they share a temperature, they were once neighbors. Inflation also flattened any curvature the way blowing up a balloon flattens its surface, predicting a flat universe that matched measurements to better than 1%. Inflation's key assumption, a substance whose density does not thin out as it expands, once sounded strange, but the Nobel-winning discovery of dark energy proved exactly that substance exists. Dark energy is driving a slow new wave of inflation right now, doubling the universe's size every 8 billion years, a gentle echo of the violent birth explosion. Finding that strange substance in the present universe was one of the most powerful confirmations a bold theoretical prediction has ever received. During inflation, microscopic quantum tremors were stretched across cosmic scales, turning subatomic fuzz into galaxy-sized density variations. Gravity then slowly pulled those denser patches together over billions of years, building every galaxy, cluster, and cosmic filament you see in the sky tonight. The predicted pattern of those quantum seeds matches measurements with remarkable accuracy. Every galaxy is, in a very real sense, a magnified quantum fluctuation. Parallel universes are not themselves a theory. They are a prediction of theories like inflation that have passed real observational tests here in our universe. Science tests a theory by checking its predictions, not by visiting every corner it describes. We accept black holes without ever jumping into one. Calling parallel universes unscientific because they are unobservable is like calling the far side of the moon unscientific before the first spacecraft flew around it. Inflation does not just produce one universe and stop. It keeps going, with inflation ending in different pockets of space at different times, each pocket becoming its own infinite universe. Each of those pockets is itself a level I multiverse, infinite in extent, making the total level 2 structure a tree that branches and branches without ever stopping. You are sitting inside one leaf of that infinite branching tree, unaware of the countless other leaves growing in every direction around you. The laws of physics you observe are really effective laws specific to your corner of the level 2 multiverse, like water being liquid here but solid or gaseous elsewhere. The truly fundamental equations, those of string theory, for instance, stay the same everywhere. Only the apparent physics shifts from pocket to pocket. What you have always called the laws of nature may be local customs, not universal laws, a thought that is both unsettling and deeply freeing. String theory contains 9 spatial dimensions, but different regions of the level 2 multiverse may unfurl different numbers of them into large, visible scales. Universes with more than 3 large spatial dimensions cannot support stable atoms or stable solar orbits. Everything falls apart before complexity can emerge. We find ourselves in a 3-space, one-time universe not because it is the only one, but because it is one of the very few where observers can exist to notice. The constants of nature, gravity's strength, the mass of the electron, the density of dark energy, look eerily perfect for producing stars, atoms, and life. If those constants vary randomly across the level 2-second multiverse, then most universes are sterile, and observers naturally find themselves only in the rare livable ones. The fine-tuning stops looking miraculous when you realize the universe was not designed for life. It is just that only life-friendly universes ever get noticed. Not long ago, even mentioning parallel universes in a physics paper could get you laughed out of a conference. That cultural attitude has shifted dramatically. The success of inflation theory, the discovery of dark energy, and the lack of any better explanation for fine-tuning have pushed skeptics to take the multiverse seriously. Even scientists who still dislike the conclusion are increasingly finding themselves unable to find a logical flaw in the argument that leads there. In quantum mechanics, a particle does not sit in one place waiting for you to find it. It exists in a smeared-out superposition of many possible locations all at once. The wave function is not made of any physical material. It is a mathematical object that encodes the probabilities of every possible outcome of every possible measurement. Reality at its smallest scale is not a collection of tiny marbles but a shimmering fog of possibilities that only sharpens when you choose to look. If an electron were squeezed all the way into the nucleus, Heisenberg's uncertainty principle would give it wildly random momentum and fling it straight back out. This simple rule is why atoms do not collapse. Confinement creates momentum, and momentum fights confinement, reaching a stable balance we call an atom. Every solid object you touch exists only because a quantum rule forbids the matter inside it from ever fully shrinking down to nothing. Scientists had carefully measured more than 20,000 lines from atoms in laboratories around the world, a mountain of painstaking data accumulated over decades. The Schrödinger equation captured every single pattern in all 20,000 lines using just 3 numbers, an extraordinary act of data compression. A theory that explains a mountain of observations with a handful of numbers is not just correct, it is pointing at something genuinely deep about the structure of nature. The Copenhagen interpretation says the wave function randomly collapses the instant you observe a particle, snapping it from many possibilities into one definite result. But critics immediately spotted a gaping hole. There is no equation telling you exactly what counts as an observation. Does a robot count? A webcam? A sleeping scientist? A theory with no clear rule for when its central mechanism triggers is not a complete theory. It is a placeholder waiting for something better to replace it. Schrödinger's cat shows that quantum superposition does not stay politely locked inside the atom. It can scale up through a chain of amplifications into the everyday world. A radioactive atom in a mixed state triggers a mechanism that places a whole cat in a superposition of alive and dead, making the quantum classical boundary vanish. If you cannot draw a clean line between quantum and classical worlds, then quantum weirdness is not a microscopic oddity. It is a feature of reality at every scale. Einstein could not accept wave function collapse because it meant the outcome of a measurement is purely random. Even perfect knowledge cannot tell you what will happen next. Physics had always been about predicting the future from the present. Randomness as a fundamental fact felt like surrendering the entire project of science. Einstein's resistance was not stubbornness. It was a deeply principled refusal to accept an explanation that left the most important question unanswered. Informal polls at physics conferences reveal a striking trend. The many worlds interpretation went from 8 votes in 1997 to 16 in 2010, while Copenhagen dropped from 13 to 0. That is not a landslide. It is a quiet revolution in how physicists think about the nature of quantum reality, playing out one conference at a time. Scientific consensus does not change overnight. It changes one persuaded physicist at a time, until the old view quietly runs out of defenders. Level through parallel universes are not far away in space. They exist right here, separated from you in Hilbert space, the abstract mathematical space where wave functions live. This makes quantum branching feel more immediate than cosmic parallel universes. It is happening all around you, not at the edge of an observable horizon. The other yous are not far away. They are, in a precise mathematical sense, right beside you, just unreachable from where you stand. Every time a quantum event gets amplified, a cosmic ray mutating a cell, a storm forming, a neuron firing, the universe branches into parallel copies. This has been going on since the Big Bang, producing more parallel histories than there are grains of sand in our entire observable universe. Almost every possible history that does not break the laws of physics has played out in some branch, including many versions of this exact conversation. The author showed mathematically that if space is infinite, level through third quantum parallel universes are just copies of outcomes that already exist far away in regular space. This means the whole bitter debate between Copenhagen and Everett interpretations ends in a kind of grand anticlimax. Both outcomes happen somewhere, either way. The philosophical fight that seemed so urgent turns out to be a question about vocabulary, not about what the universe actually does. The math of quantum mechanics is the same in every serious interpretation. What differs is only the verbal story told about what that math is supposed to mean. The simplest math, the Schrödinger equation with no exceptions added, predicts parallel worlds, and there is no experimental evidence against that simplest version. The real choice is between accepting many worlds or accepting many words, extra verbal complexity added to avoid an uncomfortable mathematical truth. The cosmological interpretation reframes quantum uncertainty not as mysterious randomness, but as a simple problem of not knowing which copy of yourself you are. If infinite space contains many identical copies of you before a quantum coin flip, you cannot know in advance which copy will see heads, so you assign a probability. Quantum randomness might not be a fundamental mystery of nature. It might be a very ordinary case of not knowing your own address in a very large multiverse. Your brain does not experience the external world directly. It builds a running model of it, a kind of dashboard that summarizes what the senses report. A car dashboard tells you speed and fuel level, but nothing about the engine's internal temperature or the precise road surface. Your brain's model is equally selective. What you experience as reality is always the map, never the territory, and the map has edges, gaps, and deliberate simplifications built in. Internal reality fails in three distinct ways: illusions, where you perceive something wrong; omissions, where you miss something real; and hallucinations, where you perceive something absent. All three types of failure happen to healthy, functioning brains. They are not bugs in broken minds, but features of how every brain processes the world. Knowing your perception can fail in these specific ways is not depressing. It is the first step toward building a more accurate picture of what is actually there. Your eyes detect only a thin sliver of the electromagnetic spectrum. Radio waves, X-rays, and gamma rays fill the universe, but your brain builds a world as if none of them exist. Even combining all animal senses on Earth, we collectively miss the subatomic world and the dark matter and dark energy that make up 96% of everything. The universe we walk around experiencing every day is a tiny, highly edited highlight reel of a vastly richer reality humming invisibly around us. Between the private inner movie and the full external reality sits consensus reality, the version of the world every observer, human or robot, agrees on. A cat, a robot, and a colorblind human may experience a door very differently, yet all agree on whether it is open. That shared fact is consensus reality. Science lives in consensus reality. It deliberately strips away the personal inner movie and keeps only what any careful observer would confirm. Understanding reality splits into two cleanly separate problems. Physics must connect external reality to consensus reality, and cognitive science must connect consensus to internal reality. Separating the problems is powerful because each one is already monstrously difficult. Combining them would make progress on either nearly impossible. Good science often advances by identifying the right way to split a hard question into manageable pieces, not just by working harder on the tangled whole. From Galileo to Newton to Einstein, thinkers have noticed that the physical world follows mathematical rules with an accuracy that seems almost impossible to explain. Nobel laureate Eugene Wigner called it the unreasonable effectiveness of mathematics, a mystery that still has no widely accepted answer. Maybe math works so well in physics not because we invented the right tool, but because we are discovering the actual structure of what the universe is made of. The mathematical universe hypothesis makes a startling claim. If you believe our universe exists independently of human observers, then you must accept it as a mathematical structure. A complete description of reality with no human baggage attached, no words, no feelings, no labels, can only be expressed as a mathematical structure. We are not using math as a telescope to peer at a separate physical world. We are self-aware pieces of the mathematical object itself, looking inward. Space is defined by dimensionality and curvature, particles by charge, spin, and lepton number. None of these properties require any non-mathematical stuff to exist. Even the wave function, more fundamental than any particle, lives entirely in abstract Hilbert space, a purely mathematical object with nothing physical beneath it. At the deepest level physicists have reached, every building block of reality turns out to have only mathematical properties and nothing more. A mathematical structure, properly understood, is a set of abstract entities whose only properties come from how they relate to each other. Nothing more, nothing less. There are no built-in labels, no colors, no meanings, just a pattern of pure relations, like a social network where what matters is who is connected to whom, not who anyone is. Mathematical structures exist independently of any mind that thinks about them. We discover them, the way explorers discover continents rather than invent them. Philosophy has long been haunted by an infinite regress. Explaining any property requires explaining the properties of the parts, which requires explaining their parts forever. The mathematical universe hypothesis offers a clean escape. At the deepest level, the parts of reality have no intrinsic properties at all, only relations between each other. All the richness of the physical world, including you reading this, emerges from a pattern of pure relations with nothing mysterious hidden underneath them. Two mathematical descriptions are considered identical if a perfect correspondence exists between their relations. The labels and symbols used are completely irrelevant. An alien civilization would discover the same 5 platonic solids humans know, even using entirely different names and notation, because the structures exist beyond any language. What mathematics is really about, at its core, is not numbers or symbols. It is the study of patterns of relation that exist independently of anyone who studies them. Einstein's spacetime picture presents the universe as a 4-dimensional block that simply exists. Past, present, and future are all equally real locations within it. The feeling that time flows, that now rushes forward leaving yesterday behind, is not a feature of the universe, but a feature of the observer moving through it. Your past does not cease to exist when you move into the future. It remains exactly where it always was, a permanent address inside the 4-dimensional block. Physics describes all matter and energy as fields, numbers assigned to every point in space-time, which means every particle you are made of is, at bottom, a number. Just as a computer encodes music as numbers without losing the music, the universe encodes matter as numbers without losing the matter, or so the hypothesis suggests. If that is true, then the entire physical world is not separate from mathematics. It is an instance of mathematics running on no hardware at all. You are not a thing moving through time. You are a self-aware pattern woven into the fabric of space-time, extended across 4 dimensions like a sculpture in time as well as space. Your sense of I flowing through a present moment is a model your brain builds, a movie playing inside the pattern, not a property of the pattern itself. That does not make you less real. It makes you a more interesting kind of real than you ever imagined, a mathematical structure that became aware of itself. If reality is a mathematical structure, nothing is ever truly created or destroyed. Those ideas require change, and change does not exist at the bird's eye view of the whole structure. The entire cosmic history from Big Bang to Final Fate is like a DVD that already contains every frame. Nothing is added as it plays, nothing is removed. Every moment you have ever lived, including this one, is permanently encoded in that eternal structure, not gone, just located at a different address in space-time. If quantum mechanics creates many parallel versions of you, predicting your personal future requires first finding every self-aware being in the entire mathematical structure. Then you need to identify which of those beings is you, a question that requires a definition of personal identity that science does not yet possess. The future of physics may depend less on bigger telescopes and more on solving the ancient philosophical puzzle of what it means to be the same you across time. Lee Smolin says time is the only truly real thing. Julian Barber says change is an illusion and time need not appear in physics at all. Brian Greene feels uneasy about giving up change. These brilliant, careful scientists hold radically different views on the nature of time, which means the question is genuinely, beautifully, still open. You have just followed a journey from the expanding cosmos to the fabric of space-time to the radical idea that reality itself is mathematics, and the adventure is only beginning.